Tonight, we're going to confront something that almost everyone gets wrong about leaving the solar system. Most people imagine it like walking through a door. You pass the last planet, you cross a line, and you're out. But the truth is far stranger and far more unsettling than that. The solar system does not end, it fades, and the journey outward is not a single dramatic exit. It is a slow, grinding loss of everything that keeps you alive. Sunlight weakens, signals stretch into silence. The protective bubble you never knew existed thins, and finally vanishes. And what waits beyond is not just emptiness, it is exposure. Raw, permanent exposure to the harshest environment the universe has to offer. By the end of tonight, you're going to understand exactly why leaving is far worse than you think. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. Most people carry a mental picture of the solar system that looks something like this. There is the sun at the center. 8 planets arranged in orbits around it. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The innermost planets are rocky and small. The outer ones are massive balls of gas and ice, and Neptune, the last of them, sits at the far edge, roughly 30 astronomical units from the Sun. 1 astronomical unit is the average distance from the Earth to the Sun, about 93 million miles. So Neptune orbits at approximately 2.8 billion miles out. That sounds like the edge. That sounds like the boundary. Past Neptune and you are outside. You have left the solar system. This is one of the most common and most dangerous misconceptions in all of astronomy. It shapes how people think about space travel, about the difficulty of reaching other stars, and about what it would actually mean to send a spacecraft or a human crew beyond our home system. It creates the illusion that the solar system is a tidy, bounded thing with a clear exit. It is not. It is not even close. The misconception feels right because it matches how we were taught to think about our cosmic neighborhood. The textbook diagrams show 8 tidy circles and then blank space. Even sophisticated animations usually zoom out past Neptune and then fade to black, as if there is nothing more to show. But there is enormously, almost incomprehensibly more. And the reason most people do not know this is that what lies beyond Neptune is invisible, dark, frozen, and scattered so thinly across such colossal distances that it does not photograph well. It does not make for dramatic images on a poster, but it is real. It is vast, and it changes everything about what the phrase leaving the solar system actually means. Neptune itself is a magnificent world. It is an ice giant roughly 17 times the mass of Earth, wrapped in an atmosphere of hydrogen, helium, and methane that gives it a vivid blue color. Winds on Neptune exceed 1,200 miles per hour. The fastest sustained winds measured on any planet in the solar system. It has at least 16 known moons, the largest being Triton, a captured object that orbits in the wrong direction and may have originated in the Kuiper Belt. It marks a real transition. Beyond it, there are no more giant planets, no more massive gravitational gatekeepers, but that transition is not an ending. Let us start with the most basic correction. Neptune is not the edge of the solar system. It is the last major planet in the solar system. Saying Neptune is the edge because it is the last planet is like saying your front door is the edge of your property because it is the last part of your house. The property goes much farther. You just cannot see it from the doorstep. Beyond Neptune, the solar system continues. And it continues on a scale that makes the planetary region look like a small huddle of objects clustered around a campfire, while the actual territory stretches out into the night in every direction for miles. The first major structure you encounter beyond Neptune is the Kuiper Belt. Named after the Dutch-American astronomer Gerard Kuiper, who speculated about its existence in the 1950s, the Kuiper Belt is a vast flattened ring of icy objects. It begins at roughly Neptune's orbit, around 30 astronomical units from the Sun, and extends outward to approximately 50 astronomical units in its densest classical form. The scattered disk associated with it reaches much farther. 50 astronomical units is about 4.6 billion miles from the Sun. So the Kuiper Belt alone spans roughly 20 astronomical units of radial distance in its main concentration. That is wider than the distance from the Sun to Uranus. Think about that for a moment. The zone just beyond the last planet is wider than the space containing most of the planets themselves. And it is far from empty. Astronomers estimate that the Kuiper Belt contains hundreds of thousands of objects larger than 60 miles across. It may contain millions of smaller bodies. These are not asteroids in the traditional sense. They are icy remnants from the earliest era of the solar system, left over from the process that built the giant planets billions of years ago. They are composed of frozen water, methane, ammonia, and other volatile compounds. Ancient building materials that never got swept up into a planet because Neptune's gravity kept them stirred and scattered rather than allowing them to coalesce into something larger. The Kuiper Belt is, in a real sense, a fossil record. It is a frozen archive of the conditions that existed in the outer solar system 4.5 billion years ago, when the planets were still forming. And it is enormous, not just in extent, but in what it tells us about how wrong our simple picture of the solar system really is. Because the Kuiper Belt is not a boundary. It is not a finish line that a departing spacecraft crosses on its way to freedom. It is a beginning. The beginning of a region that goes on and on and on, far beyond anything most people have ever been told about. Far beyond anything most educational materials have ever bothered to illustrate. The most famous Kuiper Belt object is Pluto. For 76 years, from its discovery in 1930 to the International Astronomical Union's reclassification in 2006, Pluto was considered the 9th planet. Most people alive today grew up learning this. Its reclassification to dwarf planet status was not a rejection of Pluto itself, but a recognition that Pluto is not alone out there. It is one member of a vast population, and not even the most massive. Eris, discovered in 2005, is slightly more massive than Pluto, though slightly smaller in diameter. Its discovery was one of the key reasons the astronomical community reclassified Pluto. Because if Pluto was a planet, then Eris had to be one too, and so did the growing list of similar objects being found in the same region of the solar system. Marke, Haumea, and several other bodies recognized as dwarf planets orbit in or near the Kuiper Belt. Each one is a world in its own right, with surfaces of exotic ices, faint atmospheres that come and go as their orbits carry them closer to and farther from the Sun, and in some cases, moons of their own. Pluto alone has 5 known moons. These are not featureless specks. They are complex objects, and they are scattered across a region so wide that most of them have never been visited by any spacecraft. In July of 2015, NASA's New Horizons spacecraft flew past Pluto after a journey of more than 9 years from Earth. The images it returned were stunning and revelatory. Pluto was not the dead, featureless ice ball many had expected. It had vast plains of frozen nitrogen, towering mountains of water ice rising more than 11,000 feet above the surface, a thin, haze-layered atmosphere extending over 100 miles above the ground, and evidence of geological activity that no one had predicted for a world so small and so cold. Pluto was dynamic and complex, sitting in the frozen outer reaches of the solar system, quietly defying every low expectation the scientific community had carried for decades. But New Horizons did not stop at Pluto. It continued outward into the Kuiper Belt. On January 1st of 2019, it flew past a small Kuiper Belt object called Arrokoth, a body roughly 22 miles long, shaped like a flattened snowman, orbiting more than 44 astronomical units from the Sun. Arrokoth is one of the most primitive objects ever visited by a spacecraft. It appears to have been largely unchanged since the formation of the solar system, 4.5 billion years ago. Its two lobes seem to have come together gently, not in a violent collision, but in a slow, delicate merger, offering scientists a direct window into how the smallest building blocks of the outer solar system assembled themselves before the planets finished forming. And in June of 2026, New Horizons woke from its longest hibernation in mission history. 321 days of dormancy designed to conserve power and reduce costs. The spacecraft is now approximately 63 astronomical units from the Sun, still sending back data about the Kuiper Belt environment, still pushing outward. It is heading toward a boundary that scientists predict it may reach as early as 2029. But the Kuiper Belt itself stretches far beyond where New Horizons has traveled, and Arrokoth is just one object among potentially millions. The Kuiper Belt is not a wall or a fence. It is a vast frozen debris field. Passing through it does not mean leaving the solar system. It means entering one of the solar system's most expansive and least explored territories. Now, here is where the scale begins to get truly uncomfortable. The Kuiper Belt's classical boundary at roughly 50 astronomical units sounds far, and it is far by any human standard. It is more than 4.5 billion miles from the Sun. But compare that distance to the full extent of the solar system as defined by gravitational influence, and it barely registers. The Sun's gravity does not stop at Neptune, or the Kuiper Belt, or 100 astronomical units, or 1,000. The Sun's gravitational reach extends outward until another star's gravity becomes dominant, and the nearest star system, Alpha Centauri, is approximately 4.37 light-years away. 1 light-year is roughly 63,240 astronomical units. Alpha Centauri sits at approximately 276,000 astronomical units from our Sun. The gravitational boundary of the solar system, the point where the Sun's pull gives way to the pull of neighboring stars, lies somewhere around 100,000 to 200,000 astronomical units, depending on direction and the mass distribution of nearby stellar neighbors. This means that by gravitational definition, the solar system's radius is roughly 1 to 2 light-years. Let that settle for a moment. Neptune is at 30 astronomical units. The gravitational edge of the solar system is at approximately 100,000 astronomical units or beyond. Neptune sits at less than 1/3 of 1/10 of 1% of the way to the true boundary. Passing Neptune is not leaving the solar system. It is barely stepping off the porch. And this is not an obscure technicality. It matters because the space between Neptune and the true outer reaches of the solar system is not empty, not safe, and not short. It is an almost inconceivably vast territory filled with hazards, isolation, and conditions that get relentlessly worse the farther out you travel. Beyond the Kuiper Belt's main concentration, the scattered disk extends outward. Objects in the scattered disk have orbits that carry them hundreds of astronomical units from the Sun at their most distant points, plunging back to near Neptune's orbit at their closest. These are bodies that were flung outward by gravitational interactions with Neptune billions of years ago, and now travel on enormous looping paths through the outer darkness, spending most of their time in the cold, far reaches of the solar system where sunlight is barely a memory. One of the most extreme known scattered disk objects is Sedna. Discovered in 2003, Sedna orbits the Sun on an extraordinarily elongated path. At its closest approach, it comes no nearer than about 76 astronomical units. That is more than twice Neptune's distance. At its farthest point, it swings out to roughly 937 astronomical units from the Sun. Its orbital period is estimated at more than 11,000 years. A single trip around the Sun for Sedna takes more than twice as long as all of recorded human civilization. Sedna is so distant that the Sun from its surface would appear as little more than an extremely bright star. Brighter than anything else in the sky, certainly. Unmistakably the dominant point of light. But not the blazing disk we see from Earth. Not a source of meaningful warmth. Not a power source you could use. And not a beacon you could navigate by with any confidence from much farther out. Sedna sits at the edge of what we can currently detect, and it is not even close to the most distant objects bound to our solar system. Beyond the scattered disk, in a transitional zone sometimes called the Hills Cloud, objects may orbit the Sun at distances of 2,000 to 20,000 astronomical units. These are so far away, so faint, and so slow-moving against the background stars that we have almost no direct observations of them. We infer their existence from the comets they occasionally send inward, long-period comets that take thousands or tens of thousands of years to complete a single orbit, arriving from directions that suggest a roughly spherical source population surrounding the Sun at enormous distance. That source population is the Oort Cloud, and the Oort Cloud is where the true scale of the solar system becomes almost impossible to hold in your mind. The Oort Cloud is a hypothesized spherical shell of icy objects surrounding the entire solar system. Its inner edge may begin as close as 1,000 astronomical units from the Sun, though many estimates place it nearer to 2,000. Its outer edge, according to NASA, is estimated at around 100,000 astronomical units. Some estimates push it even farther. 100,000 astronomical units is approximately 1.5 light years. That means the Oort Cloud's outer boundary may extend more than a third of the way to the nearest star. No telescope has ever imaged the Oort Cloud. No spacecraft has come within a fraction of a percent of reaching it. Its existence is inferred entirely from the behavior of long-period comets and from mathematical models of how the solar system formed. But the inference is strong and widely accepted. Long-period comets arrive from every direction, not just from the plane of the planets. This tells astronomers that the source region must be spherical rather than flat, wrapping around the sun in all directions rather than sitting in a disk like the Kuiper Belt. And the orbital characteristics of these comets consistently point to a vast reservoir of icy bodies at distances measured in tens of thousands of astronomical units. Scientists describe the Oort Cloud as having two distinct regions. The inner Oort Cloud, sometimes called the Hills Cloud, extends from roughly 2,000 to 20,000 astronomical units. Objects here tend to have orbits that are more influenced by the sun's gravity and less disturbed by passing stars. The outer Oort Cloud, from roughly 20,000 to 100,000 astronomical units or beyond, is more spherical and more vulnerable to gravitational perturbations from the galaxy itself, from passing stars, from giant molecular clouds drifting through the Milky Way. It is the outer Oort Cloud that sends long-period comets plunging toward the inner solar system when a gravitational nudge from a passing star shifts an icy body onto a new trajectory. The Oort Cloud as a whole may contain trillions of objects. Its total mass is estimated at roughly 1 to several times the mass of Earth, spread across a volume of space so enormous that density is almost meaninglessly low. You could fly through the Oort Cloud for centuries and never come close to a single object. It is a cloud in name only. In practice, it is an abyss with a few frozen specks drifting through it on orbits so long that a single trip around the sun takes longer than most human civilizations have lasted. Now, consider what all of this means for a spacecraft heading outward. Voyager 1, the most distant human-made object, is currently approximately 167 astronomical units from the Sun, traveling outward at roughly 3.5 astronomical units per year. It has been flying since 1977. Almost 5 decades of flight at roughly 38,000 miles per hour. And it has not yet reached even 0.2% of the distance to the Oort Cloud's outer edge. At its current speed, Voyager 1 would take approximately 300 years to reach the inner edge of the Oort Cloud, and approximately 28,000 years to cross it entirely. By comparison, all of recorded human history spans only about 5,000 years. Voyager would need more than 5 times the length of everything humans have ever written down just to cross the outermost structure of the solar system. And during that entire crossing, Voyager would still be inside the solar system by gravitational definition. Still bound to the sun, still orbiting, however slowly, around the same star it launched from in 1977. It would not be in interstellar space in the fullest sense. It would be in the solar system's most remote, most hostile, most unreachable territory. So when someone says a spacecraft has left the solar system because it passed Neptune, they are not just slightly wrong. They are off by a factor of thousands. They are mistaking the last building on the block for the edge of the continent. The planetary region, everything from Mercury out to Neptune, spans 30 astronomical units. The full solar system, out to the Oort Cloud's estimated edge, spans roughly 100,000 astronomical units or more. The planets occupy 0.03% of the solar system's total radial extent. Everything else, more than 99.97% of the distance, lies beyond Neptune in a frozen, dark, mostly unexplored wilderness that most people do not even know exists. This is the first and most important thing to understand about leaving the solar system. The exit is not where you think it is. It is not past the last planet. It is not past the Kuiper Belt. It is not even past a boundary called the heliopause. The true outer limit, if there even is a clean outer limit, lies at a distance so extreme that no technology we currently possess or can realistically envision would reach it within a single human lifetime. And every mile of that distance brings new problems. The sunlight fades, not suddenly, not at a wall, but steadily, relentlessly, according to the inverse square law. Double your distance from the sun and the sunlight you receive drops to 1/4 of its previous intensity. At Neptune, 30 astronomical units out, sunlight is already roughly 900 times weaker than it is on Earth. Noon on Neptune receives less light than deep twilight here. Move farther out into the Kuiper Belt, and it weakens still. By the time you reach the distances where Sedna orbits, the sun is a point of light. Brilliant against the background stars, but no longer a disk you can resolve with the naked eye. And it only gets dimmer from there. At 1,000 astronomical units, sunlight is 1 million times weaker than at Earth. At 10,000 astronomical units, it is 100 million times weaker. At the Oort Cloud's outer edge, the sun would still be visible, likely among the brightest stars in the sky, but its light would carry no practical energy. You could not power anything with it. You could not warm anything with it. You could not use it for much beyond a rough navigational reference, and even that becomes harder as you move farther out, and the sun dims into the crowded field of the stellar neighborhood. This is a fundamental constraint that shapes everything about deep space travel. Solar power, the energy source that sustains most missions in the inner solar system, becomes useless beyond roughly Jupiter's orbit at 5 astronomical units. Every spacecraft that operates in the outer solar system relies on nuclear power, specifically radioisotope, thermoelectric generators that convert the heat from decaying plutonium-238 into electricity. These generators are reliable. They have no moving parts. They work in total darkness, but they are not permanent. They lose approximately 4 watts of electrical output per year as the plutonium decays. After a few decades, they can barely power a handful of instruments. After a century, they would be dead. Voyager 1's generators launched with approximately 470 watts of electrical power in 1977. Today, they produce fewer than 200 watts, and that number continues to drop every year. Both Voyager spacecraft have had to shut down instruments one by one to conserve what little remains. In 2025, NASA switched off Voyager 1's cosmic ray subsystem, the very instrument that had helped confirm its crossing into a new region of space a decade earlier, purely to save power. Each shutdown is a painful trade, buying the mission another year or two of life at the cost of losing another sense, another way of perceiving the environment it travels through. NASA hopes to keep the remaining instruments running through the spacecraft's 50th anniversary in 2027, but the margin is razor thin. The most distant human-made objects in existence are slowly going dark, not because anything broke, not because of any collision or malfunction, but because the physics of radioactive decay is quietly, inevitably taking away their voice, and power is not the only thing that fades. Communication fades too. Voyager 1's radio signal currently takes more than 22 hours to reach Earth. In November of 2026, that delay will cross a full 24 hours, one light day, making Voyager the first human-made object to reach that distance. A command sent to Voyager in the morning would not receive a response until 2 days later. And this is at roughly 167 astronomical units. At 2000 astronomical units, near the inner reaches of the Oort Cloud, a signal would take more than 11 days each way. At the outer edge, 100,000 astronomical units, it would take more than a year. Communication does not just slow down, it stretches towards silence. Any future spacecraft heading beyond the planets would face the same constraint. You can carry nuclear fuel, but it decays on a fixed schedule no engineer can change. You can build larger generators, but they add mass, and mass demands more fuel to accelerate, which adds more mass. You can design more efficient electronics, but efficiency has physical limits that no clever design can overcome entirely. At some point, the power runs out, and when it does, the spacecraft goes silent. No more data, no more transmissions, no more communication with home. Just a dead machine drifting through the dark on a trajectory that will carry it outward for millions of years, long after every trace of the civilization that built it has disappeared. This is the reality that the simple mental model of the solar system hides from you. The planets are not the solar system. They are a tiny, well-lit cluster at the center of something enormously larger. Beyond them lies a territory so vast, so cold, so dark, and so silent that crossing it would take longer than any machine humanity has ever built could survive. And any living crew aboard such a machine would face every one of these problems and more, compounded by the biological demands of keeping human beings alive in conditions that grow more hostile with every passing astronomical unit. And we have not even talked about the most important thing the sun does for everything inside that territory. Because the sun is not just a light source, it is not just a gravitational anchor holding the planets in their orbits. It is actively doing something else, something extraordinary, something most people have never heard of. It is generating an invisible shield that wraps around the entire solar system and protects every planet, every moon, every asteroid, every spacecraft, and every living thing within it from one of the most dangerous forces in the galaxy. That shield has a name. It has a structure. It has boundaries that spacecraft have actually crossed and measured. And losing it is where the true danger of leaving the solar system begins. The sun is burning. Right now, as you listen to this, our star is converting roughly 620 million metric tons of hydrogen into helium every single second. That is a nuclear furnace beyond human comprehension. The temperature at the sun's core is approximately 27 million degrees Fahrenheit. The energy released per second is equivalent to roughly 400 trillion watts, and a portion of that energy does not stay inside the sun. It escapes, not as light, though light escapes too. It escapes as something else entirely. Something most people have never thought about, even though it is the reason every living thing on Earth has not already been killed by radiation from the galaxy. The sun exhales, constantly, in every direction. At all times, even when the sun appears calm through a filtered telescope, a continuous, violent, high-speed stream of charged particles pours outward from the sun's outer atmosphere and races into space. The outer atmosphere is called the corona, a superheated halo of plasma that extends millions of miles above the visible surface. The corona is paradoxically far hotter than the surface itself, reaching temperatures of several million degrees Fahrenheit, compared to the surface's roughly 10,000 degrees. This extreme heat gives the particles in the corona enough energy to escape the sun's gravity entirely and stream outward into space in every direction. The result is a constant outward flow of protons, electrons, and alpha particles called the solar wind. And it is not gentle. It moves at speeds ranging from roughly 250 miles per second in its slower form to over 500 miles per second in its fastest gusts. That translates to roughly 900,000 to nearly 2 million miles per hour. The solar wind does not stop at Earth, or Mars, or Jupiter, or Neptune, or the Kuiper Belt. It keeps going, streaming outward past every planet, past every asteroid, past every dwarf planet and frozen body in the outer solar system, moving farther and farther into the void. But it does eventually stop. Not because it runs out of energy in a sudden, dramatic way, but because it runs into something. Far out beyond the planets, the solar wind encounters the interstellar medium, the thin gas and dust and magnetic fields that fill the space between the stars in our galaxy. The interstellar medium has its own pressure, its own particle flow, its own magnetic structure. And at some point, far from the sun, the outward push of the solar wind is balanced and then overcome by the inward pressure of this interstellar material. The result is a bubble. An enormous, invisible magnetic bubble inflated by the solar wind, stretching far beyond the orbit of every planet, enclosing the entire solar system inside it. This bubble is called the Heliosphere, and it is one of the most important structures in the solar system that almost nobody talks about. The heliosphere is not a solid shell or a wall. It is more like a region of influence, a zone where the sun's outward flowing particles and magnetic fields dominate the local environment. Inside the heliosphere, the solar wind controls the conditions. Outside it, the interstellar medium takes over. The boundary between the two is not a clean line, but a transitional region, messy and turbulent and dynamic, shifting with the solar cycle and the changing pressure of the surrounding galaxy. But here is the crucial thing. The heliosphere is not just a curiosity for space physicists, it is a shield. And what it shields us from is genuinely dangerous. Out beyond the heliosphere, filling the space between the stars, there is a constant rain of high-energy particles called galactic cosmic rays. These are not the gentle photons of starlight. They are atomic nuclei, mostly protons, but also heavier nuclei including helium, carbon, iron, and others, accelerated to extraordinary energies by the most violent events in the galaxy. Supernova explosions, the shock waves from dying massive stars, the environments around pulsars and the remnants of stellar cataclysms that occurred millions or even billions of years ago. These particles have been accelerated to speeds approaching the speed of light, and they carry enormous energy for their size. Some galactic cosmic rays carry individual particle energies millions or even billions of times greater than anything produced by human-made particle accelerators. The most extreme cosmic rays ever detected carry the kinetic energy of a fast-pitch baseball concentrated into a single subatomic particle. These particles are traveling so close to the speed of light that the difference is measured in decimal places too deep for ordinary notation. These are among the most energetic individual particles in the known universe, and they are everywhere in the galaxy outside the shielded regions around stars. When a galactic cosmic ray strikes biological tissue, it does not pass through harmlessly. It ionizes atoms along its path, tearing electrons away from molecules, breaking chemical bonds, and damaging DNA. The most energetic cosmic rays can penetrate deep into material, passing through spacecraft walls, through shielding, through the human body, leaving a trail of molecular disruption behind them. On Earth, we are almost entirely unaware of this bombardment because we are protected by 3 overlapping layers of defense. The first and outermost layer is the heliosphere itself. The solar wind and the sun's magnetic field embedded within it deflect and slow many incoming galactic cosmic rays before they ever reach the inner solar system. The heliosphere does not block all cosmic rays. The most energetic ones punch through regardless, but it significantly reduces the flux, the number of cosmic ray particles reaching the vicinity of the planets. During periods of high solar activity, when the solar wind is stronger and the heliosphere's magnetic field is more tangled and turbulent, the cosmic ray flux inside the heliosphere drops measurably. During solar minimum, when the wind is calmer and the field is smoother, more cosmic rays penetrate inward. This inverse relationship has been confirmed over decades of observation. The second layer is Earth's own magnetic field, the magnetosphere. Earth generates a dipole magnetic field from its molten iron core, and this field extends thousands of miles into space, forming a protective cavity around the planet. Charged particles, including those cosmic rays that make it past the heliosphere, are deflected by this field, guided away from the surface and channeled toward the poles. The magnetosphere is the reason the auroras exist. Charged particles funneling along magnetic field lines toward the polar regions collide with atmospheric gases and produce light. The auroras are beautiful, but they are also a visible signature of a protective system doing its job, diverting particle radiation that would otherwise reach the surface. The third layer is the atmosphere itself. Even the cosmic rays that penetrate both the heliosphere and the magnetosphere still have to pass through roughly 60 miles of atmospheric gas before reaching the ground. Most of them interact with atmospheric molecules along the way, producing cascades of secondary particles that dissipate their energy before reaching the surface. By the time this radiation reaches sea level, it is reduced to a tiny fraction of what arrives at the top of the atmosphere. So here on Earth, sitting at the bottom of a deep atmospheric ocean, surrounded by a planetary magnetic field, nestled inside the sun's heliospheric bubble, we experience only a faint whisper of the cosmic ray bombardment that fills the galaxy. We absorb a small background dose of radiation from cosmic rays every day, but it is low enough that our biology can handle it. Our cells repair the damage, our bodies evolved under this exact level of exposure. But strip away any one of those layers and the picture changes. Strip away the atmosphere and radiation exposure on the surface increases dramatically, which is one of the many reasons the surface of Mars is so hostile to unprotected life. Strip away the magnetosphere and the atmosphere itself begins to erode, as the solar wind strips away atmospheric particles over geological time. This is likely what happened to Mars. Roughly 4 billion years ago, Mars had a thicker atmosphere, possibly liquid water on its surface, and potentially conditions that could have supported life. But Mars lost its global magnetic field early in its history, and without that protection, the solar wind gradually stripped away the atmosphere molecule by molecule over hundreds of millions of years. Today, what remains is a thin wisp of carbon dioxide, far too thin to shield the surface from radiation, far too thin to sustain liquid water. Mars is a cautionary example of what happens when even one protective layer disappears. Strip away the heliosphere, the outermost layer, the first line of defense and something worse happens, you are exposed to the full, unfiltered galactic cosmic ray flux, not the reduced, softened version that trickles through the heliosphere. The raw, full-strength bombardment from every supernova remnant, every stellar shockwave, every violent event in the Milky Way that has ever accelerated particles to relativistic speeds. This is what awaits any spacecraft that leaves the heliosphere, and it is one of the most serious hazards of interstellar travel that rarely gets the attention it deserves. Now, let us look at the heliosphere's structure more carefully. Because it is not a simple bubble with a single wall, it has layers, and each layer marks a distinct change in conditions for anything passing through it on the way out. The solar wind leaves the sun and streams outward at supersonic speed. For billions of miles, it moves unimpeded, a steady, fast, outward flow. But far from the sun, somewhere between roughly 80 and 100 astronomical units, depending on direction and the phase of the solar cycle, the solar wind encounters increasing resistance from the interstellar medium pressing inward. At a certain distance, the solar wind can no longer maintain supersonic speed. It abruptly slows down, compresses, and heats up. This transition is called the termination shock, and it is the first major boundary of the outer heliosphere. The termination shock is not a fixed surface. It is not a line drawn permanently on a map at a set number of astronomical units. It breathes, it moves, it responds to the sun's activity in real time, with a delay of roughly a year for changes in the solar wind to propagate outward to the shock's location. During solar maximum, when the sun is more active and the solar wind is stronger, the termination shock pushes outward, sometimes significantly. During solar minimum, when solar activity drops and the wind weakens, the shock retreats inward, pulling closer to the sun. It can shift by 10 or 20 astronomical units over the course of a single 11-year solar cycle. A spacecraft approaching the termination shock could actually cross it more than once if the boundary moves back and forth across the spacecraft's position as it passes through. Beyond the termination shock is the heliosheath. This is the region where the slowed down solar wind piles up, turbulent, hot, compressed, and chaotic. The solar wind is still present here, still flowing, but it has lost its supersonic speed. It tumbles and swirls, interacting with incoming interstellar material in a complex, disordered zone that is far harder to model and predict than the clean, fast solar wind closer to the sun. The heliosheath extends outward for roughly another 20 to 40 astronomical units, though its exact thickness varies by direction and has proven difficult to model accurately. Temperatures in the heliosheath are extremely high in particle physics terms, with ions heated to hundreds of thousands or even millions of degrees, but the density is so low that a human hand placed in this plasma would feel nothing. It is hot in the sense of particle energy, not in the sense of thermal heat transfer. And then, beyond the heliosheath, the solar wind finally gives out entirely. The outward pressure of the sun's particles is matched and then overcome by the inward pressure of the interstellar medium. This is the heliopause. It is the boundary where the sun's direct influence on the surrounding plasma effectively ends. Beyond the heliopause, the environment is dominated not by the sun's wind, but by the particles, fields, and flows of the galaxy itself. The heliopause is located at roughly 120 astronomical units from the sun, based on the two direct measurements we have. That is roughly 11 billion miles. It is an enormous distance by any human standard, but compared to the full extent of the solar system as defined by the Oort Cloud, it is still relatively close to the Sun. The heliopause sits at barely 0.1% of the distance to the Oort Cloud's outer edge. It is a boundary within a much larger territory, not the outer wall of the whole structure. And the heliopause is not a wall at all. It is not a hard surface you could touch or see. It is a gradient, a region where conditions shift from solar-dominated to interstellar-dominated. The transition can be surprisingly abrupt in some places, but it is still fundamentally a zone of changing plasma conditions, not a physical barrier. You would notice no flash of light, no vibration, no audible marker. Your instruments would register the change, a spike in galactic cosmic ray counts, a drop in solar wind particle density, a shift in the magnetic field direction, but your human senses would detect nothing at all. The most important boundary in the solar system is completely invisible to direct experience. Now, scientists have long debated the shape of this bubble. For decades, most models depicted the heliosphere as a comet-shaped structure with a rounded nose facing the direction of the sun's motion through the galaxy and a long tail trailing behind, stretched out by the flow of interstellar material around it, much like the tail of a comet is stretched by the solar wind. This made intuitive sense. The sun is moving through the interstellar medium at roughly 52,000 miles per hour. Just as a boat moving through water creates a bow wave and a wake, the sun's motion should shape the heliosphere into an elongated form. But more recent research has challenged this picture. A team at Boston University, led by researcher Merav Ofer, proposed a model suggesting the heliosphere might not have a long tail at all. Instead, their simulations showed something closer to a compact shape, sometimes described as resembling a croissant, with two jet-like lobes extending from the sun's magnetic poles, rather than a single elongated tail. Further work by Dan Riesenfeld and colleagues at Los Alamos National Laboratory, using data from NASA's IBEX satellite, which detected energetic neutral atoms streaming inward from the heliosphere's boundary, produced a three-dimensional map suggesting the shape is more like a deflated crescent, neither perfectly spherical nor neatly elongated, but something more complex and asymmetric than any earlier model predicted. The key technique was a form of echolocation. They correlated changes in solar wind intensity measured near Earth with changes in the energetic neutral atom signal arriving from the boundary years later, estimating distance in different directions and building a three-dimensional picture that did not match any of the simple models. The debate is ongoing, and the shape remains one of the most actively studied open questions in heliophysics. And it matters. The shape of the heliosphere determines how effectively it shields the solar system from galactic cosmic rays in different directions. If the heliosphere has a long tail, there may be a region behind the sun where shielding is weaker. If it is more compact, shielding might be more uniform. To settle this question and many others, NASA launched the Interstellar Mapping and Acceleration Probe, known as IMAP, on September 24th, 2025. IMAP is now stationed at the Sun-Earth L1 Lagrange point, approximately 1 million miles from Earth in the direction of the Sun. From this vantage point, it maintains a constant, uninterrupted view of the space shaped by our star. The mission carries 10 scientific instruments designed to detect and map energetic neutral atoms, particles that travel in straight lines from the heliosphere's distant boundary regions back toward the inner solar system. By tracking these particles, IMAP can build a picture of the heliosphere's boundaries without physically traveling to them, essentially using the energetic neutral atoms as messengers from the edge. IMAP's instruments achieved first light in late 2025, and the mission began its primary science operations on February 1st, 2026. Early data has already shown dynamic changes in the solar wind's magnetic field and captured partial maps of the heliosphere's boundaries. For the first time, scientists may be able to watch the heliosphere breathe, expanding and contracting with the solar cycle, responding to bursts of solar activity, and interacting with the interstellar medium in ways that have only been guessed at until now. But IMAP is not the only spacecraft approaching this story from the outside. Far from Earth, heading outward through the cold reaches of the Kuiper Belt, New Horizons is on a trajectory that will bring it to the termination shock within the coming years. In June of 2026, researchers at the Southwest Research Institute published 2 scientific papers, one in Advances in Space Research and one in the Astrophysical Journal, predicting when New Horizons would cross the termination shock. Their models, combining solar wind forecasting methods with numerical simulations of the heliosphere, produced a prediction window. New Horizons could encounter the termination shock as early as 2029 or as late as 2040. The wide range reflects the genuine uncertainty in the heliosphere's behavior. The termination shock moves. It responds to the solar cycle. A strong solar maximum pushes it outward. A deep solar minimum lets it fall inward. And because the sun's future activity cannot be predicted with precision years in advance, the shock's location when New Horizons reaches it remains uncertain. What makes this prediction especially striking is that the researchers noted New Horizons could cross the termination shock more than once. As the heliosphere expands and contracts, the shock could wash back and forth across the spacecraft's position. The termination shock is not a fixed gate. It is a living, breathing frontier that can pass over a spacecraft like a tide. If New Horizons does reach and cross the termination shock, it will become only the 3rd spacecraft in human history to do so, and it carries instruments that neither Voyager carried, including a dedicated solar wind plasma detector that has already measured the gradual slowdown of the solar wind as the spacecraft moves farther from the sun. These measurements have shown that the solar wind speed is decreasing measurably as New Horizons pushes deeper into the outer solar system, consistent with the growing resistance of interstellar material pressing inward against the wind. The interaction between the solar wind and the interstellar medium is not a distant abstraction for New Horizons. It is a measurable reality. The wind is slowing. The pressure is building. The interstellar medium is making its presence felt, and with every passing year, the balance shifts a little more toward the outside. Somewhere ahead, at a distance no one can pin down to better than a decade, the termination shock is waiting. But whether New Horizons crosses it in 2029 or 2040, the fundamental picture remains the same. There is a region of space, far beyond the planets, where the sun's outward push fails, where the wind dies, where the magnetic bubble that has wrapped around everything we know finally thins and gives way. And beyond that boundary, conditions change in ways that matter enormously for anything trying to survive out there. Inside the heliosphere, galactic cosmic ray flux is reduced. The solar wind and the sun's embedded magnetic field act as a filter, a diffuse but real barrier that turns away or slows many incoming particles. The reduction is not total. Cosmic rays still penetrate the heliosphere, especially the highest energy ones, but the overall flux is meaningfully lower inside than outside. Measurements taken by both Voyager spacecraft confirm this directly. When each probe crossed the heliopause, the galactic cosmic ray count jumped sharply. The sheltering effect of the heliosphere was not theoretical. It was measured, recorded, and confirmed by instruments that had been running for decades. Outside the heliosphere, a spacecraft is exposed to the full interstellar cosmic ray environment. The radiation dose accumulates continuously. There is no natural shielding, no magnetic deflection, no particle wind pushing the worst of it away. Every day, every month, every year spent beyond the heliopause adds to the cumulative radiation exposure of the spacecraft and anything aboard it. For electronics, this means gradual degradation of semiconductor components, increased error rates in computer memory, and eventual failure of sensitive instruments. For biological organisms, it means DNA damage, elevated cancer risk, potential central nervous system effects, and long-term health consequences that compound with exposure time. Shielding can reduce, but not eliminate this exposure. Passive shielding, surrounding the crew compartment with mass, with water tanks or polyethylene blocks or metal walls, can stop lower energy cosmic rays and secondary particles. But the highest energy galactic cosmic rays are so penetrating that no practical amount of passive shielding can stop them entirely. They pass through meters of material, producing cascades of secondary particles inside the shielding that can actually increase the dose in some configurations rather than decrease it. This is called the secondary particle problem, and it is one of the most stubborn challenges in deep space radiation protection. More shielding is not always better. Beyond a certain thickness, the shielding creates more secondaries than it stops primaries, and the radiation environment inside the spacecraft can paradoxically worsen. Active shielding, using powerful magnetic or electric fields to deflect incoming charged particles, is an alternative that has been studied but never implemented on a spacecraft. The magnetic fields required would need to be extraordinarily strong and maintained continuously for years or decades, demanding enormous power and posing engineering challenges that no current design has solved. It remains a theoretical option rather than a practical one. So the heliosphere is not just an interesting boundary on a map. It is a functional shield whose loss has direct, measurable, dangerous consequences for anything that crosses beyond it. And the most unsettling part of this realization is how invisible the whole system is. You cannot see the heliosphere. You cannot feel the solar wind. You cannot sense the galactic cosmic rays that the heliosphere is deflecting. From the surface of the Earth, standing under a blue sky on a calm day, there is absolutely no perceptible evidence that any of this exists. The air feels still. The sky looks peaceful. Nothing suggests that you are standing inside a vast magnetic bubble inflated by a constant nuclear wind from a star 93 million miles away, and that this bubble is the only thing between you and a galaxy-wide bombardment of relativistic particles capable of shredding your DNA. It is like living in a house and never knowing the walls are there. You feel warmth, you feel comfort, you feel safe, and you assume that the warmth and comfort and safety are simply the natural state of things, the default condition of existence. You never consider that the walls are doing anything, because you have never been outside. You have never felt the storm that the walls are holding back. but the walls are there, and they are holding something back. And for any spacecraft heading outward, away from the sun, away from the planets, away from the Kuiper Belt, heading into the deep outer solar system and beyond, there comes a point where those walls end, where the last traces of the solar wind fade to nothing, where the magnetic field carried outward from the sun becomes too weak to deflect anything, where the heliosphere, the sun's outermost and most invisible gift to everything inside it, simply stops. That point has been reached. 2 spacecraft have crossed it. They sent back data that confirmed what models had predicted, and revealed details that no one had expected. And what they found on the other side changed our understanding of what it means to leave the sun's protection. That crossing, and everything it revealed, changed our understanding of what it means to leave the sun's protection. On August 20th, 1977, a Titan IIIe Centaur rocket launched from Cape Canaveral, carrying a spacecraft called Voyager 2. 16 days later, on September 5th, a second identical spacecraft launched on a faster trajectory. That was Voyager 1. Despite launching second, Voyager 1's trajectory was designed to reach Jupiter first, and it did, flying past the giant planet in March of 1979. Both spacecraft then continued to Saturn, and Voyager 2 went on to visit Uranus and Neptune, the only spacecraft ever to fly past either of those worlds. By the late 1980s, the planetary missions were over. Every camera and imaging system had been shut down to conserve power, but the spacecraft was still alive, still transmitting, still carrying instruments capable of measuring the particles and magnetic fields around them. And they were still moving outward, away from the sun, away from the planets, heading into the space between the stars at roughly 38,000 miles per hour. No one knew exactly what they would find. No one knew precisely where the heliosphere's boundary was. The models gave estimates, but estimates from models are not the same as measurements from instruments that are actually there. So the scientific community waited, and the spacecraft kept flying. In December of 2004, Voyager 1 crossed the termination shock at approximately 94 astronomical units from the sun. The instruments registered the change. The solar wind, which had been flowing outward at supersonic speed for the entire journey, abruptly slowed. The magnetic field strength increased. The particle environment shifted. Voyager 1 had passed from the region of fast, smooth solar wind into the heliosheath, the turbulent compressed zone where the slowed wind piles up before being stopped entirely. 3 years later, in August of 2007, Voyager 2 crossed the termination shock at a different location and a different distance, approximately 84 astronomical units. That 10 astronomical unit difference between the two crossings was itself a discovery. It confirmed that the termination shock is not a perfect sphere centered on the sun. It is asymmetric, pushed closer to the sun in some directions, and farther in others by the pressure and magnetic field of the interstellar medium flowing around the heliosphere. The shape of the boundary depends on which direction you leave. Both spacecraft then spent years traveling through the heliosheath, that hot, turbulent, chaotic zone between the termination shock and the heliopause. The heliosheath turned out to be stranger than expected. The magnetic field inside it did not behave the way models predicted. It was tangled, unsteady, filled with regions of different density and temperature. Some researchers described it as foamy, with magnetic bubbles roughly 100 million miles across, forming and reforming as the slowed solar wind churned and folded over itself, The magnetic field lines, which flow outward from the Sun in relatively orderly spirals inside the termination shock, appeared to twist and reconnect in the heliosheath, creating isolated pockets of magnetism disconnected from the broader solar field. The Sun's influence was still present, but no longer organized, no longer coherent, no longer in control. The heliosheath was a dynamic, unstable environment that defied the clean predictions of earlier theoretical work. And the spacecraft had to travel through it for years before reaching the next boundary. And then came the crossing that changed everything. On August 25th, 2012, Voyager 1 crossed the heliopause at approximately 122 astronomical units from the Sun. The moment did not announce itself with fanfare aboard the spacecraft. There was no alarm, no flash, no physical sensation. What happened was visible only in the data. And even in the data, the crossing was initially unclear. What the instrument showed was this. Over a period of just a few days, the count of galactic cosmic rays, high-energy particles arriving from outside the solar system, jumped dramatically. Simultaneously, the count of lower energy particles associated with the solar wind dropped to near zero. The solar wind, which had been a constant companion for the entire 35-year journey, effectively vanished. The environment around Voyager 1 shifted from solar-dominated to interstellar-dominated in a remarkably short span. But there was a complication. The magnetic field direction did not change as dramatically as many models had predicted. Some scientists expected a sharp rotation in the magnetic field as Voyager crossed from the Sun's magnetic domain into the interstellar magnetic field. The rotation was subtler than expected, and this led to a period of genuine scientific debate. Had Voyager 1 actually crossed the heliopause, or had it entered some intermediate region, a transitional layer that was not yet fully interstellar? The stakes were high. This would be the first confirmed detection of a spacecraft entering interstellar space. Getting it wrong in either direction, declaring the crossing prematurely, or failing to recognize it when it happened, would be a significant error in the history of space exploration. Papers were published arguing both positions. The data was reanalyzed, reinterpreted, debated at conferences, and in journal pages. Ultimately, the cosmic ray and particle data proved definitive. The sudden disappearance of solar wind particles and the corresponding surge in galactic cosmic rays was the signature of a boundary crossing. In September of 2013, more than a year after the actual event, NASA officially announced that Voyager 1 had entered interstellar space. The announcement was made by Edward Stone, the Voyager project scientist who had been with the mission since before launch. He had waited 36 years for that moment, but the full picture did not come from Voyager 1 alone. It came from its twin. Voyager 2 crossed the heliopause on November 5th, 2018, at approximately 119 astronomical units from the Sun, and Voyager 2 carried something Voyager 1 did not: a working plasma science instrument. Voyager 1's plasma instrument had failed back in 1980 during the Saturn encounter, decades before it reached the heliopause. Without it, Voyager 1 could not directly measure the density and speed of the plasma around it. Voyager 2's instrument still worked, and what it revealed at the heliopause was striking. The transition was sharp, far sharper than many models had predicted. The density of the plasma changed abruptly over a distance that was remarkably thin, far narrower than the hundreds of millions of miles some simulations had suggested. On one side of the boundary, the plasma was recognizably solar in origin, flowing outward, carrying the sun's magnetic signature. On the other side, the plasma was denser, slower, and interstellar in character, part of the material that fills the space between the stars in our region of the Milky Way. The changeover happened across a boundary so narrow that some descriptions called it almost membrane-like, a zone where solar wind plasma gave way to interstellar plasma with very little mixing in between. Researchers had expected a broad, gradual transition, a slow blending of solar and interstellar material over tens of millions of miles. Instead, the boundary was comparatively crisp. Not a solid wall, certainly, but not the diffuse, drawn-out fade that many had anticipated either. Voyager 2's plasma data also revealed that the interstellar medium just outside the heliopause was not as uniform as some models predicted. There were density variations, temperature fluctuations, and magnetic field structures that suggested the local interstellar medium has its own complex weather, shaped by the winds and explosions of other stars, by the rotation of the galaxy, and by processes that are still being studied. The temperature of the plasma also changed. Particles on the interstellar side were measured at extremely high energies, leading some popular accounts to describe the heliopause region as a wall of fire. That phrase is misleading. The particle energies are indeed high, but the density is so extraordinarily low that there is no thermal sensation, no heat in any human perceptible sense. A spacecraft passing through this region would register the energetic particles on its instruments, but would feel nothing. The wall of fire exists only in the language of particle physics, not in the experience of anyone or anything passing through. Together, the instruments painted the most complete picture ever assembled of the boundary between the sun's domain and the galaxy beyond. The magnetic field rotated. The cosmic ray count spiked. The solar wind particles vanished. And the plasma density changed, all within a narrow corridor of space. 2 crossings, 6 years apart, at 2 different locations, by 2 differently equipped spacecraft. Together, they confirmed that the heliopause is real, that it is measurable, that it is not uniform, and that it marks a genuine transition from one physical environment to another. But here is the part that most news coverage of the Voyager crossings did not emphasize enough. Crossing the heliopause does not mean leaving the solar system. Not by every definition, not even by most definitions. The heliopause marks the edge of the sun's wind, at the boundary where the sun's outward flow of particles is finally halted by the interstellar medium. That is a meaningful boundary. It is the edge of the heliosphere, the end of the sun's plasma bubble, and by the definition used in heliophysics, it is the point where interstellar space begins. But the sun's influence does not end at the heliopause. The sun's gravity extends far beyond it. Every object in the Oort Cloud, thousands and tens of thousands of astronomical units from the sun, is still gravitationally bound to the sun, still orbiting it, still, by the gravitational definition, inside the solar system. Voyager 1, at roughly 167 astronomical units, is well past the heliopause but nowhere near the Oort Cloud. It has left the sun's magnetic and particle environment. It has not left the sun's gravitational domain. It is in interstellar space by one standard and still inside the solar system by another. This layered, overlapping set of definitions is not a technicality. It is central to understanding what leaving the solar system actually means, and why the common phrase Voyager has left the solar system is both true and deeply misleading at the same time. By the heliophysics definition, Voyager 1 is in interstellar space. It has left the sun's plasma bubble. The particles around it are interstellar, not solar. That is real. That is measured. That is confirmed. By the gravitational definition, Voyager 1 is still inside the solar system. It is still bound to the sun's gravity. If it had no velocity at all, it would fall back toward the sun. It has not escaped the sun's gravitational well. It is still, in the language of orbital mechanics, a satellite of our star. By the structural definition, Voyager 1 has not even reached the outermost known structure of the solar system. The Oort Cloud lies ahead, vast and unexplored. And Voyager will take centuries to reach its inner edge, and tens of thousands of years to cross it. There is no single exit. There is no one boundary where everything changes at once. Instead, there is a sequence of transitions, each one marking the loss of a different form of the sun's influence, each one separated from the next by enormous distances. First, you leave the planets, then you leave the Kuiper Belt, then you lose usable sunlight, then you cross the termination shock, then you cross the heliopause and lose the heliosphere's cosmic ray shielding, and then, stretching ahead of you for thousands and tens of thousands of astronomical units, there is still the Oort Cloud, still the sun's gravity, still the slow fade of everything that connected you to home. Each transition is a loss, and no single crossing marks the moment you are truly out. Voyager 1 is the farthest any human-made object has ever travelled, and by one critical measure, it has barely begun. Now let us turn to what all of this means for any spacecraft, or any crew, heading deeper outward. Because beyond the heliopause, everything that was already difficult becomes harder. Every system that was already strained is strained further, and several new problems appear that do not exist closer to home. Power fades, communication delays grow. But there is an aspect of communication that delay alone does not capture, and that is signal strength. Voyager's transmitter operates at roughly 22 watts. That is less than the power of a refrigerator light bulb. That tiny signal has to cross billions of miles of empty space and arrive at Earth with enough energy to be detected by the Deep Space Network, a collection of massive radio dishes in California, Spain, and Australia, each one 70 meters across. Even with those enormous receivers, the signal that arrives from Voyager is phenomenally weak. It is measured in units so small that they are almost abstract. The signal from Voyager 1 arriving at Earth is roughly 20 billion times weaker than the power needed to operate a digital watch, and the signal gets weaker with distance. Radio signals, like light, obey the inverse square law. Double the distance and the signal strength drops to 1/4. Triple it and the signal drops to 1/9. Voyager 1 is currently at roughly 167 astronomical units. If it were at the inner edge of the Oort Cloud, 2,000 astronomical units, the signal will be roughly 140 times weaker than it is now. At the outer edge, 100,000 astronomical units, it would be approximately 360,000 times weaker. No existing receiver on Earth could detect it. The spacecraft could be functioning perfectly, transmitting data as reliably as the day it launched, and Earth would hear nothing. Silence. Not because the spacecraft stopped talking, but because the distance swallowed its voice. Any future interstellar mission would need dramatically more powerful transmitters or entirely new communication architectures. Perhaps laser-based optical communication instead of radio, or relay stations positioned along the route to boost and forward signals. None of these exist today. And building them would itself be a multi-generational engineering challenge, requiring infrastructure spread across tens or hundreds of astronomical units of space. Navigation is another problem that intensifies beyond the heliopause. Inside the solar system, spacecraft navigate using a combination of methods. Radio tracking from Earth provides precise position and velocity data. Star trackers on the spacecraft identify known stars and calculate orientation. And the gravitational influence of the Sun and planets can be modeled to high precision, allowing trajectory calculations that are accurate over years. Beyond the heliopause, several of these methods degrade. Radio tracking still works as long as the signal is detectable, but the round-trip time for a ranging signal grows to days and then weeks, making real-time navigation updates impossible. Star trackers still function, but as the spacecraft moves farther from the Sun, the apparent positions of nearby stars shift due to parallax, the change in viewing angle caused by the spacecraft's changing position. A star that appears at one angular position when viewed from Earth appears at a slightly different position when viewed from 100 astronomical units away. The closer the star, the larger the shift. Star catalogs compiled from Earth become progressively less accurate as the spacecraft moves outward. At 1,000 astronomical units, the nearest stars have shifted noticeably against the background. At 10,000 astronomical units, the entire local stellar neighborhood looks subtly rearranged. The constellations, which are projections of a three-dimensional star distribution onto a two-dimensional sky, as seen from one specific location, begin to distort. Familiar patterns stretch, compress, and ultimately lose their recognizable shape. The navigation software has to account for these shifts using three-dimensional stellar models rather than two-dimensional sky maps, and any errors in the stellar distance database propagate directly into navigation errors that grow with every additional astronomical unit traveled. Gravitational modeling also becomes harder. Inside the solar system, the gravitational field is dominated by the Sun, with well-characterized contributions from the planets. Beyond the heliopause, the gravitational environment is simpler in some ways. The Sun's pull is weaker and the planets are negligibly far, but it is also less well known. The distribution of mass in the Oort Cloud is uncertain. The gravitational influence of nearby stars, while small, is not zero. And over journeys lasting centuries, tiny gravitational perturbations that are undetectable at launch can accumulate into significant trajectory deviations. A spacecraft navigating through the outer solar system would need autonomous navigation capability. It could not rely on instructions from Earth, because those instructions would arrive too late to matter. It would need onboard systems capable of measuring its position and velocity independently, calculating corrections, and executing them without human intervention. Those systems would need to function flawlessly for decades or centuries, and if they failed, there would be no way to fix them. The spacecraft would drift, gradually deviating from its intended course, possibly missing its destination by millions or billions of miles. Temperature management is a quieter challenge, but it compounds everything else. The ambient temperature in interstellar space is approximately 2.7 Kelvin, just a few degrees above absolute zero. This is the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. Any object in interstellar space that is not generating its own heat will eventually cool to this temperature. Spacecraft electronics are designed to operate within specific temperature ranges. too cold and lubricants freeze, metal contracts, solder joints crack, batteries lose capacity, and electronic components behave unpredictably. Voyager's heaters, powered by its dwindling generators, have kept critical systems within operating range for decades. But as the generators weaken, the heaters are among the systems being turned off to conserve power for the instruments. The spacecraft is slowly getting colder. Components that have operated reliably for nearly 50 years are approaching temperatures they were never tested at. Every degree below the design range increases the probability of a failure that no one can repair. For a crewed mission, temperature management would be even more critical. Human beings cannot survive at 2.7 Kelvin. The habitat must be heated, insulated, and maintained at a comfortable temperature for the entire journey. Every watt of heating requires power. Every insulation panel adds mass. And over a journey measured in decades or centuries, the cumulative energy required to keep a habitat warm in the deep cold of interstellar space is enormous. Any interruption in heating, even brief, could be fatal to the crew and damaging to systems that cannot be replaced. And then there is the problem that underlies all others: the impossibility of rescue. On Earth, if a ship sinks, you send another ship. If a plane crashes in remote terrain, you send a search party. If an astronaut on the International Space Station has a medical emergency, a Soyuz capsule can bring them home to Earth in hours. Even on the surface of Mars, if we ever establish a presence there, a rescue mission from Earth could arrive in months. The distances are large, but they are traversable within human planning horizons. Beyond the heliopause, rescue is not difficult or expensive or impractical. It is physically impossible within any meaningful time frame. No technology that exists or is under serious development could reach a spacecraft in the outer solar system in any useful period. A mission launched from Earth at Voyager's speed would take decades just to reach the heliopause. At the speeds achievable by the most advanced propulsion concepts currently under study, it would still take years. And that assumes the rescue mission launches immediately upon learning of the emergency, which it cannot, because the distress signal itself takes hours or days or weeks to arrive, depending on distance. By the time Earth learns there is a problem, the emergency is already that old, and any response would not arrive for years or decades after that. If a critical system fails at 200 astronomical units, no replacement part is coming. If a crew member suffers a medical emergency that the onboard medical team cannot handle, no hospital ship is on the way. If the hull is breached by a micrometeorite, no repair crew can be dispatched. Whatever happens, the people aboard that spacecraft must solve it with what they have on hand, or it does not get solved. This is a qualitatively different situation from any other human endeavor. Polar expeditions were remote, but resupply was theoretically possible. Submarine crews are isolated, but they surface eventually. Even Apollo astronauts, 250,000 miles from Earth, were only a few days from home. A spacecraft beyond the heliopause is months from the nearest planet, years from Earth by signal, and decades or centuries from any conceivable rescue mission. The crew is alone in the most absolute sense the word has ever carried. Every system on the spacecraft becomes a single point of potential failure, with no external backup. Life support, power, water recycling, food production, navigation, communications, hull integrity. If any of these fails in a way that the crew cannot repair using only onboard resources, the mission ends. Not with a dramatic rescue, not with a last-minute save. It ends quietly in the dark, billions of miles from anyone who could help, in a silence that would not be noticed on Earth for years. And all of these challenges, power loss, signal fade, navigation drift, thermal stress, radiation exposure, and the impossibility of rescue, do not arrive one at a time. They compound, they overlap, they reinforce each other. A power loss reduces heating, which stresses components, which increases the probability of a navigation failure, which makes course correction harder, which extends the journey time, which increases radiation exposure, which degrades electronics further. The failures cascade. Each problem makes every other problem worse. And the farther from the sun you travel, the tighter the cascade becomes. Because every resource is more constrained, every margin is thinner, and every backup is closer to its own limit. This is what Voyager's crossing revealed, not just in what the instruments measured, but in what the mission's slow decline demonstrates. Voyager is dying, not from a single dramatic failure, but from the gradual, compounding erosion of every system that keeps it alive. Power fading, heaters shutting down, instruments going dark one by one, like gauges on a dashboard winking out as the engine runs dry. And Voyager is a simple machine. No crew, no life support, no food or water or air to maintain. Just electronics, a transmitter, and a power source. It has no biological needs, no psychological demands, no medical emergencies. And still, after less than 50 years and less than 200 astronomical units, it is approaching the end of its operational life. And the fragility is not hypothetical. In November of 2023, Voyager 1 stopped making sense. The spacecraft, 15 billion miles from Earth, began transmitting a steady stream of unreadable data. The radio link was intact. The probe was receiving commands. But its flight data subsystem, one of 3 onboard computers built in the 1970s, could no longer package its science and engineering telemetry into anything the Deep Space Network could decode. For 5 months, Voyager 1 spoke gibberish. The cause turned out to be a single failed memory chip. One chip, holding roughly 3% of the computer's memory, had gone bad, likely damaged by a cosmic ray strike or simply worn out after 46 years in space. The chip could not be repaired. No one could go out and replace it. The spacecraft was billions of miles beyond any conceivable service call. JPL engineers broke the corrupted code into fragments, searched for empty corners in the remaining memory, rewrote the chunks so they would still function as a whole, and beamed the patch to a spacecraft so distant that each command took 22.5 hours to arrive. Every test was a 2-day commitment. The engineers who designed the original software had largely retired or died. The documentation was nearly half a century old, and the computer they were reprogramming had less memory than a modern car key. On April 20th, 2024, Voyager 1 returned readable data for the first time in 5 months. Science data followed by June. That episode happened at 167 astronomical units, barely past the heliopause, practically next door by the standards of the journey we are describing. And it nearly ended the mission. A single chip, a few corrupted kilobytes. At any greater distance, with any weaker signal, the diagnosis might have taken longer than the spacecraft had power to wait. Now imagine a crewed vessel. Imagine all of Voyager's problems plus the staggering additional complexity of keeping human beings alive, healthy, fed, hydrated, breathing, warm, and psychologically intact across the same distances and the same timescales. The engineering challenge does not scale linearly. It multiplies. Every human need adds systems. Every system adds failure modes. Every failure mode requires contingency planning and spare parts and expertise and power. Voyager crossed the heliopause at 122 astronomical units. That crossing took 35 years from launch. And from the heliopause, the journey outward is only beginning. The Oort Cloud's inner edge may still be 1,000 astronomical units away or more. At Voyager's speed, that is another 300 years. And the Oort Cloud itself stretches for tens of thousands of astronomical units beyond that. The solar system does not end at the heliopause. It continues, vast and dark and cold, for distances that dwarf everything the Voyager spacecraft have crossed so far. The heliopause is not an exit. It is the moment the last active protection fails. Beyond it, there is no shield against galactic radiation. Beyond it, the sun's influence continues only as gravity, a silent, invisible pull that grows weaker but never quite disappears, holding the frozen bodies of the Oort Cloud in orbits so long that a single revolution takes longer than human civilization has existed. Everything a spacecraft needs to survive, power, warmth, communication, navigation, shielding, and the ability to repair itself must be carried from home and maintained without help across distances that make every previous human journey look like a walk across a room. And the deepest truth that Voyager's journey tells us is this: the crossing was not the hard part. The hard part is everything that comes after. Imagine you are aboard a spacecraft. You have passed the last planet. You have crossed the Kuiper Belt. You have watched your power reserves dwindle and your communication windows stretch. You have passed through the termination shock, through the heliosheath, through the heliopause. The instruments confirm what the data has been showing for months. The solar wind is gone. The galactic cosmic ray count is high and steady. The magnetic field around you belongs to the galaxy now, not to the sun. And ahead of you, there is nothing visible. No landmark, no structure, no destination you can see with your eyes or point to with your finger. Just stars. The same stars that have been there the whole time, scattered across the black in every direction, unchanging in any way your senses can detect. You are moving at tens of thousands of miles per hour, and yet nothing around you appears to move at all. The journey feels like standing still in an infinite room with no walls, no floor, no ceiling, and no door. The only evidence that you are moving at all comes from the instruments. Numbers on a screen telling you that your distance from the sun increases by roughly 3.5 astronomical units every year. The numbers change, everything else stays exactly the same. Behind you, the sun is still there. You can find it if you know where to look. It is bright, clearly brighter than most other stars in the sky. From 150 astronomical units, the sun is still intensely bright. A piercing point of light far more brilliant than a full moon seen from Earth, far outshining everything else in the sky. You could not mistake it for an ordinary star. It is obviously your sun, even from this distance, but keep going. At 500 astronomical units, something strange happens. The sun is still brilliant. In fact, it is still brighter than a full moon as seen from Earth. An intense, searing point of light that stands out unmistakably against the background of stars. No other star comes close to it, and yet the light it sends your way, spread across the vast sphere of distance, delivers roughly 250,000 times less energy per square meter than it does at Earth's orbit. If you held your hand up toward it, you would feel nothing. No warmth, no sense of daytime. The brightest point of light in your sky is now useless to you. You can see your sun blazing and obvious, but it cannot do anything for you anymore. That is a strange kind of loss. Not an absence, but a taunt. At 1,000 astronomical units, the sun is still roughly as bright as a full moon seen from Earth. You could not miss it. It burns in the sky like a diamond, thousands of times brighter than any star, immediately obvious to anyone who looks up. But it is a point now, not a disk. And though its light reaches you, its energy does not. The sunlight falling on your spacecraft is 1 million times weaker than at Earth. No solar panel ever built could convert this into usable power. The sun is still the most prominent thing in your sky, and it is completely, irreversibly useless to you. You can see home, brilliant and unmistakable, and it cannot help you. There is something in that contradiction that carries a weight no distance figure can convey. The sun has not disappeared. It has simply stopped being the sun in any sense that matters for survival. It is a lighthouse with no harbour, a signal with no rescue behind it. At 10,000 astronomical units, the sun is still brighter than Venus, at its most brilliant as seen from Earth. Still easily the most prominent point of light in the sky. Still, if you know anything about stars, obviously not a star at all, but something closer. Something that outshines everything around it by a factor of more than 100. You can still find your sun without instruments. You can still point to it and say, that one, that is where I came from. But the sunlight reaching you is now 100 million times weaker than at Earth. The temperature of any surface facing the sun is indistinguishable from any surface facing away. The sun's contribution to your energy budget, your warmth, your shielding, your survival is zero. You are looking at the brightest light in your sky, and it is doing nothing for you. Not because it has gone dim, because you have gone too far. The sun does not become just another star until you approach the outermost edge of the Oort Cloud, roughly 100,000 astronomical units out. Only there, at approximately 1.5 light years, does its apparent brightness finally drop to something comparable to the brightest stars seen from Earth. Only there does the sun stop being obviously, unmistakably yours, and begin to blend into the stellar field. The visual dominance of the sun and the gravitational dominance of the sun end at almost exactly the same distance. That is not a coincidence. It is the scale of what you are leaving. This is where the Oort Cloud lives. And this is the territory that any spacecraft leaving the solar system must still cross after everything else. The Oort Cloud's dimensions are staggering on paper, but the numbers alone do not convey what crossing it would actually mean. So let us try to make the experience concrete. The inner edge of the Oort Cloud may begin as close as 1,000 astronomical units from the sun. At the speed of the fastest spacecraft ever launched, roughly 38,000 miles per hour, reaching this inner edge from the heliopause would take approximately 3 centuries. 300 years of flight through empty space, with no landmark, no structure, no measurable change in the environment around you. 300 years during which the only evidence that you are moving comes from the instruments. The stars do not perceptibly shift on human timescales. The darkness does not change. The cold does not deepen because it is already as cold as it will ever get. There is nothing to see, nothing to hear, Nothing to feel except the steady hum of whatever machinery is still running, and the silence beyond the hole. And after those 300 years, you have reached only the inner edge. The Oort Cloud stretches ahead for tens of thousands of astronomical units more. If its outer boundary lies at 100,000 astronomical units, as most estimates suggest, then crossing the Oort Cloud at Voyager speed would consume a span of time so long it makes a recorded history look like a single afternoon. Every dynasty, every empire, every constitution and calendar and chronicle ever committed to record could fit inside the crossing with room to spare many times over. The Great Pyramid of Giza was built roughly 4,500 years ago, and it is one of the oldest monumental structures still standing. The spacecraft would not have crossed even a quarter of the Oort Cloud in that time. Empires would rise and fall. Languages would be born and go extinct. Entire civilizations would flourish and vanish, and leave no trace except ruins that would themselves erode to nothing. And the spacecraft would still be inside the Oort Cloud, still inside the solar system, still gravitationally bound to a star that had long since dimmed to just another point of light behind it. During all of that time, the spacecraft would almost certainly encounter nothing. The Oort Cloud contains perhaps trillions of objects, but they are scattered across a volume of space so vast that the average distance between them is measured in millions of miles. Flying through the Oort Cloud is not like flying through a cloud of debris. It is like flying through an empty ballroom that happens to contain a few grains of sand suspended in the air at random positions. You would pass through the entire structure without coming close to a single object. The Oort Cloud is a cloud only in the statistical sense. In the experiential sense, it is indistinguishable from the void. And yet, it is real. Its objects are out there, frozen bodies of ice and rock on orbits so slow and so vast that a single revolution around the sun takes tens of thousands of years. Some of these bodies have been falling toward the sun since before Homo sapiens existed and have not yet completed their first pass. They move through the darkness on trajectories shaped by the gravity of a star they have never been close to in any meaningful sense, and they will continue moving on those trajectories long after every trace of human civilization has disappeared. At some point, at the very outer reaches of the Oort Cloud, the sun's gravity becomes so weak that the gravitational pull of neighboring stars begins to compete with it. This is the true gravitational edge of the solar system. Not a sharp line, not a wall, not even a transition you could measure with instruments aboard a passing spacecraft, but a gradient. A zone where objects are no longer clearly bound to the sun, where a slight perturbation from a passing star or a drift in a giant molecular cloud could pull an icy body free and send it wandering into interstellar space. No longer orbiting anything, no longer part of any system, just drifting through the galaxy on its own indefinite trajectory. This outer boundary is estimated at roughly 100,000 astronomical units, approximately 1.5 light years from the sun. Beyond it, the sun is just another star, not the center of a system, not the anchor of a family of planets, just one yellow point of light among the roughly 200 billion stars in the Milky Way galaxy. And what is out there beyond this final edge? The interstellar medium, the gas and dust and magnetic fields that fill the space between the stars. It is not empty. It is extraordinarily thin, far thinner than any vacuum achievable in a laboratory on Earth. But it is not nothing. There are roughly 100,000 to 1 million hydrogen atoms per cubic meter of interstellar space in the sun's neighborhood. Compare that to the roughly 25 trillion molecules per cubic meter in Earth's atmosphere at sea level, and the interstellar medium is practically a void. But it extends for light years in every direction, and it has structure. It has regions of higher density and lower density. It has magnetic fields threaded through it by the remnants of ancient stellar explosions. It has a temperature a few thousand Kelvin in warmer regions, just a few Kelvin in the coldest molecular clouds. The Sun is currently traveling through a region of the interstellar medium called the local interstellar cloud. A small patch of slightly warmer, slightly denser gas, roughly 30 light-years across. This cloud is itself embedded within a much larger structure called the local bubble, a vast cavity in the interstellar medium roughly 1,000 light-years across that was carved out by a series of supernova explosions millions of years ago. The interior of the local bubble is relatively empty compared to the average interstellar medium, filled with extremely thin, hot gas that offers little resistance to anything passing through it. We happen to live in a cosmic clearing, a region where the gas between the stars has been swept away by ancient explosions, leaving behind a low-density environment. This is both fortunate and isolating. Fortunate because the low density of the local bubble may contribute to the heliosphere's ability to maintain its structure. Isolating because it means the nearest regions of significantly denser interstellar material are hundreds of light years away. The gulf between stars has its own geography, and the geography around our sun happens to be one of comparative emptiness. A spacecraft that truly left the solar system would find itself in this environment. A thin haze of hydrogen and helium, laced with traces of heavier elements, threaded with magnetic fields, bathed in the faint glow of distant stars and the cosmic microwave background radiation left over from the beginning of the universe. It would be the most isolated, most exposed, most vulnerable any human-built object has ever been. No heliosphere to deflect cosmic rays. No sun close enough to provide power or warmth or even a navigational reference brighter than any other star. No planet within reach. No possibility of rescue, resupply, repair, or return. This is what leaving the solar system actually means. Not a single dramatic moment. Not a flash of crossing. Not a clean exit through a defined gate. It is a long, slow, compounding process of losing everything the sun provides, one layer at a time, across distances so vast that the journey itself would outlast the entire history of the species that launched it. Let us walk through the losses in order, because the sequence is what makes this so much worse than the simple version of the story suggests. You leave Earth. You have the full sun, full power, full communication, the magnetosphere around you, the atmosphere below you, the heliosphere far above. Everything is protected. Everything works. You pass Mars. Sunlight has dropped to less than half of Earth's intensity. Solar power is weaker but still usable. Communication delay is measured in minutes. You are still well within the heliosphere, still shielded, still connected. Communication delay exceeds an hour round trip. You are deep inside the heliosphere, but already far enough from home that real-time conversation with Earth is impossible. Everything you say takes minutes to arrive. Every response takes minutes to return. The rhythm of human dialogue is broken. From here on, communication is messaging, not conversation. You pass Neptune. Sunlight is 1/900th of Earth's intensity. Solar power is completely useless. You are dependent on nuclear generators that are already aging, already losing output, already on the clock. Communication delay is over 4 hours each way. A round-trip exchange takes more than 8 hours. You have left the last planet, but you have not left anything else. The heliosphere surrounds you. The Kuiper Belt stretches in every direction. The solar system extends ahead for distances that would take tens of thousands of years to cross. You cross the Kuiper Belt. Sunlight continues to fade. Communication delays grow to 6, 8, 10 hours each way. You are moving through a region of icy remnants, frozen debris left over from the solar system's formation that extends for billions of miles in every direction. Dwarf planets orbit here in the dark, worlds that were once called planets themselves, circling the sun on paths that take centuries to complete. And still, even after crossing this entire vast region, you are inside every definition of the solar system. The heliosphere still surrounds you. The sun's gravity still dominates everything around you. The true edge is not closer. It is unimaginably far ahead. You reach the termination shock. The solar wind around you abruptly slows. The environment becomes turbulent, chaotic. You enter the Helios sheath. You are still inside the heliosphere, but the clean, fast solar wind you have traveled through for your entire journey is gone. The shielding is weakening. You cross the heliopause. The solar wind vanishes. The cosmic ray count jumps. The magnetic field rotates. You have left the sun's plasma environment. You are, by one important definition, in interstellar space. But you are still gravitationally bound to the sun. You are still inside the Oort Cloud's vast domain. You are still, by broader and equally legitimate definitions, inside the solar system. And you have lost the single most important shield between you and the full radiation environment of the Milky Way galaxy. From this point forward, every cell in your body, every circuit in your electronics, every molecule in your spacecraft structure is exposed to a bombardment that will not stop, will not weaken, and will not pause for the rest of the journey. You continue outward. The sun dims. Your power source, if it is nuclear, is decaying on a fixed schedule. Your signal is fading below detection thresholds. Your navigation system is working with star charts that are less and less accurate as parallax distorts the positions of nearby stars. Your thermal systems are fighting a losing battle against the cold. The few spare parts you carried are being used. The expertise needed to maintain critical systems is being stretched thinner with every passing year. You enter the Oort Cloud. There is nothing to see, nothing to encounter, nothing to measure except the faint background hiss of cosmic radiation and the unchanging cold. Just the slow, grinding passage of time, measured in centuries and then millennia, through a region of space so vast that it dwarfs everything you have already crossed combined. The sun is still bright behind you, still the most prominent point in the sky, but it is doing nothing for you, and it grows a little fainter with every passing decade. The destination star, if there is one, is a dim star ahead of you, growing brighter so slowly that the change is undetectable across a human lifetime, and the distance between them is filled with nothing but the thin gas of the interstellar medium, the faint hiss of cosmic rays, and a cold so deep it sits only a few degrees above the lowest temperature the universe allows. And finally, after thousands or tens of thousands of years, you reach the outer edge of the Oort Cloud. The sun's gravity no longer holds the objects around you. You are, at last, outside the solar system by every definition. Outside the planets, outside the Kuiper Belt, outside the heliosphere, outside the gravitational sphere of influence, outside everything that connected you to the star you came from. And what was on the other side? More space, more cold, more radiation, more emptiness. The nearest star is still light years away. Years of travel at the speed of light, decades or centuries at any speed a spacecraft could achieve. The journey is far from over. It has, in a real and sobering sense, only just entered its longest and most desolate phase. This is the truth that the title of tonight's journey points toward. Leaving the solar system is far worse than most people think, not because there is a single terrible barrier to cross, but because there is no barrier at all. There is only a fade, a long, slow, irreversible fade from the warmth and light and protection of the sun into the cold, exposed, unshielded environment of the galaxy. The solar system does not have a door. It does not have a wall. It does not have a moment where you step across and something changes all at once. What it has is a gradient of fading light, a gradient of weakening gravity, a gradient of thinning magnetic protection, a gradient of stretching silence. And the terrifying thing about a gradient is that there is no single moment when you can say it is over. It just keeps getting worse, dimmer, quieter, colder, more alone. Until the sun is a memory, a coordinate in a database, a dot among billions of dots, and the protection it once gave you is a fact you remember but can no longer feel. Every planet we have ever known, every sunrise, every blue sky, every ocean, every breath of wind, all of it exists because of a series of protections that the sun provides. Light, warmth, gravity to hold an atmosphere, a magnetic wind to push back the radiation of the galaxy, a bubble of influence that wraps around every world we have ever touched and says, inside here the conditions for life are possible, outside they are not. Leaving the solar system means leaving all of that behind, not in a single step, not at a single wall, but gradually, over distances so vast they swallow entire centuries of travel, losing one layer after another until there's nothing left. No shield, no warmth, no signal home, no way back. Just the interstellar medium, the cosmic rays, and the unimaginable distance to the next star, where a different sun might or might not have wrapped a different set of planets in a different bubble of protection. We often imagine interstellar space as a thing to cross, a gap between here and there, an obstacle to overcome on the way to somewhere else, a distance you endure in order to arrive. But interstellar space is not a gap. It is the default state of the universe. It is what most of space actually looks like, most of the time, in most directions. The solar system, with its warmth and its light, and its planets and its heliosphere and its careful layered protections, is the exception. It is a tiny, fragile, temporary island of habitability in an ocean of radiation and cold that extends in every direction for light years before you reach the next island. And even the next island, if it exists, may not have a heliosphere as strong as ours, may not have a planet with a magnetic field, may not have the conditions that made life possible here. Most stars do not have what ours has. Most of the galaxy is not like home, and the shore of that island is not a sharp line. It is a long, shallow slope that descends into the water so gradually you do not realize you are swimming until the land behind you has disappeared below the horizon. That is what leaving the solar system is. Not a plunge, not a leap. A slow wade into deeper and deeper water until the ground beneath your feet is gone and the shore behind you is out of sight and the only direction left is forward, into the open ocean, with nothing but what you carry. The Voyager spacecraft are on that slope right now, still descending, still sending back faint whispers from the shallows near the edge. Still alive, barely after nearly 50 years of continuous flight. They will go silent soon. Their power will fail. Their heaters will shut down. Their transmitters will fall quiet. And they will continue outward, dark and cold and silent, for millions of years, drifting through the Oort Cloud, and eventually, after an almost incomprehensible span of time, beyond it. They will pass into the interstellar medium and become part of the galaxy's vast inventory of small, dead, drifting objects. Anonymous specks moving through the darkness on trajectories shaped by the gravity of stars they will never orbit. Voyager 1 will pass within roughly 1.6 light-years of a star called Gliese 445 in approximately 40,000 years. It will not stop. It will not slow down. It will not orbit. It will not arrive in any meaningful sense. It will simply drift past, unnoticed and unmarked by any observer, carrying a golden record that no one may ever play, bearing a message from a species that lived on a small rocky world orbiting an ordinary yellow star in a quiet arm of a spiral galaxy. A species that looked outward and wondered, and built something small enough to fit on a spacecraft, and brave enough to send it into the void. And the void received it, and kept going. The void always keeps going. That is what the void does. There is no moment of arrival in interstellar space, no welcoming signal, no change in scenery, just more of the same emptiness stretching ahead for light years, for parsecs, for distances that make even the Oort Cloud look intimate. The next star is not waiting. It is not close. It is simply there, somewhere in the dark, separated from you by a gulf so wide that light crossing it grows measurably older during the journey. The solar system is our home, not just Earth, the whole system. The sun that powers it, the heliosphere that shields it, the gravity that holds it together, the warmth that makes chemistry possible, that makes liquid water possible, that makes biology possible. All of it, from the innermost orbit of Mercury to the outermost frozen body, drifting at the edge of the Oort Cloud, is one structure, one system, one interconnected, layered, ancient, and fragile set of conditions that makes life as we know it possible. We didn't build it, we did not choose it. We were born inside it, and we have never known anything else. Every sunrise, every season, every breath of air exists because this system works, because the sun burns, because the wind blows outward, because the bubble holds. Leaving it means losing all of those conditions. Not at once, not cleanly, not at a wall or a gate or a border you can point to on a map. It means watching them fade, one by one, over distances that test the limits of language and imagination, until the last trace of the sun's influence is gone, and you are truly, finally, irreversibly outside. And the deepest truth of this journey is that the solar system does not end. It does not have an edge in the way a cliff has an edge, sharp and definitive and impossible to miss. It fades, it thins, it lets go of you slowly, reluctantly, over light years of distance, like a hand releasing its grip one finger at a time. That fade is what makes leaving so much worse than anyone imagines. Not a wall to break through, not a line to cross, not a door to close behind you, just a slow, quiet, irreversible loss of everything that made the journey possible in the first place. The light, the warmth, the shield, the signal, the connection, the way home. And perhaps that is what we needed to understand tonight. Not just that leaving is hard, or that the distances are large, or that the dangers are real, but that the solar system is not a container with an inside and an outside. It is a condition, a set of circumstances, created by a single ordinary star that made it possible for a small rocky planet to hold liquid water and breathe air and grow forests and produce minds curious enough to ask what lies beyond. Every one of those circumstances weakens as you move outward, and none of them have a switch. None of them turn off at a boundary. They dim, they thin, they fade, until what made you possible is no longer what surrounds you. The solar system is not a place you leave. It is a protection you lose, layer by layer, mile by mile, year by year, until the sun is just a star, and the stars are just the dark, and the dark is all there is. And once it is gone, it is gone. Good night.